Hello to everyone. Today I'll be discussing the quantum mechanical formulation of Frank-Condon principle. And if there is a transition between two electronic states and corresponding to there, once we have a wave function psi double prime and psi prime for the ground state and the excited state, and then it is this total transition, that is the dipole momentum transition, that total how this dipole transition matrix value of is r depending, that will decide. So the transition moment matrix elements are transition moment r. So I'll be representing with the help of this r is equal to this psi prime of star. This matrix is m, that is dipole moment, then psi double prime of d tau, equation number of 1. M is an electric dipole moment having the component, that is, it's a dipole moment, so components will be this xi and ei. So ignoring this molecular rotation of the molecular rotation and then applying this Born-Affiner separation of the electronic and the vibrational coordinates by putting simply that the psi is equal to, you have the psi e of psi nu. So we are ignoring that this rotational wave function, but just we'll be considering that this psi is equal to in a component this wave function divided in two parts, electronic part and this vibrational part. For the dipole moment can be separated into the electric and the electric component Me and the nuclear component. And now in the same fashion, that is M can be divided into two parts, this M of E plus of M of N, that is the electronic and this nuclear one. So now once you are putting these quantities in your equation number 1, then simply you could write this R is equal to this psi of E prime and psi of nu prime star M of E plus M of N and psi of E double prime psi of nu double prime d tau E and d tau of N volume elements. So this d tau of E and d tau of N are the respectively the elements of the volume of the space and the electronic coordinates and the nuclear coordinate. It is the space coordinates and for the nuclear coordinates. So I can expand this. Now the psi of E prime and psi nu prime, this M of E, psi of E double prime of psi N, psi nu of double prime, and dt of E and dt of d in R plus psi of E prime and psi nu of prime M of N psi of E double prime psi of nu double prime dt of d tau of E and dr. So in place of d tau n, I'm writing this d of r because this nuclear charge only depending that because the vibrational, that is the nuclear wave function psi nu depending on the internuclear distance r only. So this d tau n is replaced by dr. So now the nuclear dipole moment Mn is independent coordinate of electrons. This M of n is independent of my coordinates of the electrons. It is depending on only the r. So now in the second equation, this part I could write simply this psi of E prime star psi of E double prime d tau of E and psi of nu prime and M of n psi of nu double prime of dr. We could write this part in this fashion because this is independent to this one, it is depending only dr, so we can write in this function in this way. Now this quantity is equal to 0 because you have two orthogonal states, that is if these are the orthogonal states. So because the electronic wave functions belonging to the different electronic states, so the molecules are orthogonal. So this is because we know that is psi double psi prime and psi double prime d tau is equal to 0, because these are the orthogonal wave functions. So now we are left with this transition moment. Transition moment R is in this fashion now, dr. So in general, electronic wave function psi e varies with internuclear distances r. However, it may be assumed that psi e varies very slowly with respect to the r. Means psi e is generally depending on this r, and it is very slowly depending on this r, how it varies. So once it is done, I could write this r is equal to psi of e prime and m of e psi of e double prime and d tau of e and psi of nu prime star psi of nu double prime of dr. So because we are considering that the psi of is very slowly varying function of this r, so that is why we are separating these functions in this fashion, because m of e is depending only this tau volume element, not in psi of r. That is why we are separating it. So this quantity is my electronic dipole transitions. This is my electronic dipole transitions Re. So this quantity I am writing this R of E and psi of nu prime star and psi nu double of dr and nu prime and nu double prime. So in this relation now, this quantity I am replacing this transition electronic transition moment, this Re, and then you have this function. So actually this psi e and hence Re depends on some extent on the r. Up to some extent, this is depending on this my r. The wave mechanical formulas of Frank-Condon principle rest on the assumption that the variation of Re with r is slow, that Re may be approximated by the average value of Re. So it is because it is varying with respect to this as well. So what we can approximate in this wave mechanical aspect of the Frank-Condon principle. So we can write this moment, this nu prime of nu double prime is equal to Re average of psi of nu prime star and psi nu double prime of dr. So rather than putting this electronic one, because it's depending on, because we have separated out this part and we will define that integral with the help of this Re. Now this Re is slowly varying function of this Re itself. That is why we are taking this average value of it, because this is an approximation one. And just because psi nu is equal to psi nu of star, so we can remove this one. For the electron, these vibrational states, you have the real functions. So the average electronic transition moment Re bar governs by the intensity of the band system as a whole. The relative intensities of the various bands of this system mainly depends on the square of this overlap integral. Means that the square now this change is depending on the square of this quantity. How exactly this quantity, which is the integral over a product of the, which is the integral over the product of the vibrational wave function of the lower electronic state and the upper electronic state. And it is it is called the Frank-Condon factor Q, and this quantity is called the Frank-Condon factor. So this quantity, squaring of this one, this Q of nu prime of nu double prime is equal to integration of psi prime of nu psi of nu double prime of dr its square. So this is called the Frank-Condon factor, and squaring of this is providing you that how much this total transition moment is R is there. So how much this overlap that this will define this how these two wave function, because it's the inner product, simply it is an inner product. So in a continuous basis, then how this is overlapped with another means that's what we do in the vector algebra itself. Once you are taking the dot product, it is providing the how much they are overlapped. In the same fashion that it is the inner product, and this will be providing how much they are overlapped. So if this quantity is high, then you have a transition is the transition moment is very high, then you have an intense line are appearing. So the amount of the overlap and the value of Frank-Condon factor depends on the relative position of the maxima of the nodes of the vibrational wave function psi of nu in each of the two combining electronic states, consequently upon the relative shape of and the position of the corresponding potential energy curve. Now in this figure, now what I have shown that at level nu is equal to 0, at level nu is equal to 0 for the low electron state has a central maxima, whereas above nu is equal to 0, we do not have the central maximum corresponding to this Re. And it has one prominent maxima slightly inside each turning points at a smaller maxima in between. So and once we are moving for the higher states, so we have the maxima towards this these turning points, and we have slightly, we do not have the maxima in the center of it. So if you look at in this diagram, so if I will calculate overlap, if because the transition electronic transition are taking place for the vertical one, so if I will take the product of this function, overlap of this function, so I'll be getting that corresponding to psi is equal to 0 for psi nu of double prime, having the maximum overlap with this psi nu prime is equal to 2, because the maximum value of this wave function is here. So for this one you have the transition is maximum, so that is why you will be getting that this lines light corresponding to this. This is the reason why you are getting that this nu prime is equal to 2, the transition is taking place, nu double prime is equal to 0. For this one you are getting the sharp line. If you remember, for the last class, in a last class I was discussing that for the atom of CO atom, you have a transition 0 to 2. That is the progression 0 to 2. We have a maximum intensity of the band. So this most probable transition is this one, because the wave function are the maximum, because that moment, that is the overlap is maximum for this case. You have here as well, you have a but slightly less, but the transition. So that is why you are getting this intensity of the lines are not equal, they are unequal, that depending on the how much this overlap is taking place. Then if the overlap is perfect, that is the transition, this factor, this Q factor is a maximum, then you have a maximum intensity of the lines. So in general we can conclude a vibrational transition will have a large Frank-Condon factor only if one of the two turning points of a level of one electronic state lies at approximately the same nuclear distance as one of the two turning point of the level of other electronic state, except case of the nu is equal to 0, level for which the middle point of the level rather than the turning point must be substituted. So that we need to see that at the same intermolecular distance, at the same molecular distances, now except this nu is equal to 0, where we have the maxima in the center, apart from that, for the higher states you have the maxima are not in the center, you have the depending on that potential on how these are made, because for this one you have this Re for this first excited state or the excited electronic state. So it will defining that how their overlap is taking place. So generally at the turning points, so we'll see that as I said that in the turning points, at the turning points how this is shaping. So this is the quantum mechanical expression already we have discussed in the earlier as well. Now this way we can define that how this Frank-Condon factor is responsible, how the overlap of these vibrational functions are taking place, that these overlap amount will be deciding that what is the intensity of your vibrational lines. So then again in detail, once I will illustrate with, for the rest of the molecules what we have done in the previous class, that for the three molecules, this O2, CO, and I2, and corresponding to them, we will be plotting these energy diagrams, and we'll see that how these wave functions are overlapped perfectly. That corresponding to that, we are getting these sharp lines, high intense line. On the other hand, we have the other probabilities are also there. For them, we are getting the slightly lesser intense light or the bands for them. So now the next class I will be discussing that the intensity distribution in absorption band from the Frank-Condon principle. Thank you.